So I'm going to record today's lecture as I do. We're going to talk about beta oxidation today. Then we've got basically 2 more weeks of new content. On the 21st, we'll be doing a review for exam number 3. The 28th, we'll be doing a final exam review. And then your final exam, I'll have to check and confirm this, is April 30th. I have to check and confirm because I'm looking at the Canvas page. It has it on there, but I didn't list the time, which is a little bit makes me think, oh, maybe that's not the actual time. And I put a placeholder time in there. So I'll have to square that. I will have your exam grades all squared away before our Wednesday class. I really apologize for the delay on that. Now, with that in mind, though, I'm going to go ahead and get cracking. So, I hope you enjoyed your weekend. I hope that the semester winding down isn't too chaotic or stressful for you. So, I know that this might be a time whenever you're getting lots of exams or lots of projects kind of ramping up or anything and things like that. Um, I will publish it after class today. I apologize. Yeah. So I will post the PDF and the PowerPoint later today. Um, so what we've got, lipids and metabolism, or metabolism of lipids. Just to kind of touch base on lipids, well, they're major parts of membranes. They are also major energy stores, and that's what we're really going to be focusing on. Roughly 38 kilojoules per gram of lipids, or sorry, you get approximately 38 kilojoules of energy from 1 gram of lipid. Now, the significance of that is roughly 2 times the energy that you get from a carbohydrate. CHO is a shorthand way of writing carbohydrate. Um, Now, you've probably seen this same sort of ratio, but maybe using different terms. Specifically, I'm thinking about um, calories per gram, or yeah, calories per gram. This is kilojoules as opposed to calories, but essentially it's the same thing. Um, I so I will post the. I'm sorry I don't have the PDF or the PowerPoint posted to our Canvas site. I will post them later this evening. I got a private message I'm responding to. In addition to that, lipids are fairly inert. Despite the fact that they have an acid end, they are going to be relatively inert because most of the importance of them is the hydrocarbon chain. Approximately 30 to 60% of your typical person's dietary calories are coming from lipids or fats. 90% of dietary lipid is going to be in the form of a triacylglycerol or triacylglycerols. TAG or triacylglycerol is glycerol and a fatty acid. Now we've talked about glycerol. Could I get in the chat the number of carbons that glycerol has? 3. And what did we talk about glycerol? What was one of the pieces of context in which we used or we talked about glycerol? We use glycerol for the production maybe of what? Okay, NADH. Not quite. I'm thinking about glycerol. Yeah, you would. Yeah, DHAP is what I'm looking for. We can use that DHAP so that we could then ultimately produce glucose. Now, saponification is the industrial process where you take a triacylglycerol and break it down. So glycerol is an output of that, but when we think about this from the like dietary perspective, well, I want you to think about glycerol as DHAP to glucose, and then I'm going to write in parentheses here through gluconeogenesis. Okay. In addition to that, we also talked about fatty acid chains. 16:0. Okay, so I'm going to take a moment. I apologize. I did not do this earlier. I just so that I don't have this happen anymore. I got another message from somebody who needs the PowerPoint. So I'm going to go ahead and I'm just going to go ahead and save this file. And I will be uploading the PDF in just a moment. I apologize, folks. The day got away from me, and here we are. And this is what happened. So give me just 1 second. I really appreciate you guys' patience on this. While I'm doing this, does anyone have a pick on who's going to win the big basketball game tonight? Add it to the chat. Today is the 7th. Oh, go Cougs. Houston. Okay, okay, okay. Da, 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 da. Okay. Okay, that file's there. Here I am about to, that's the PDF link. About to drag and drop the PDF. It's a small file, it's 3 MB, so it should be droppable and there without too much of an issue. Okay, we've covered basketball. Does anyone have a plan of what they're eating for dinner? Okay. I can't tell what that is, Megan. If I had to guess, seaweed salad, because it kind of looked greenish. Chipotle. Minecraft meal, hopefully. Kale seaweed salad's not too far off. Okay, I'll count that. Sam, I hear you. There's a radio show out of Austin. It's called Booker, Alex, and Sarah. It's pretty awful, but they have this feature where they talk about what their jam is, and it's kind of bland because genuinely it's like, what is something that you like? Um, and they have like a what's your jam? And then they come on like, oh, what's your jam, Booker? And it'll be like, I really like Tostitos. And they'll be like, awesome. And so right now I bring that up because my jam, if I were on Booker, Alex, and Sarah, my jam would be um, apples and peanut butter. Um, because And just so you guys know this about me, and again, I really appreciate your patience. The files are up, whether it's the PowerPoint or the PDF, they're both up. Um, this is okay, so we got some Hangry Joe's, Annie's mac and cheese, whatever I can find in the fridge. Okay, butter chicken. I saw that was a good one. Good, 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 good. Um, I'm a crunchy peanut butter person. Um, and then I have this weird, I don't know why, but my entire adult life, as long as I've purchased my own groceries, um, I've put peanut butter in the refrigerator. And I don't know why. I hardly need to because that stuff is it's never getting it's never going to get contaminated by bacteria. Okay. So, here we go. We've covered food, we've covered Booker, Alex, Sarah. Um I'm not going to end class on that note. Instead, we're going to come back to talking about lipids and fatty acids. We talked about the structures of fatty acids. 16:0 means that we've got 16 carbons, 0 double bonds. Then we've got oleic acid, linoleic acid, alpha linolenic acid, which is an omega-3 fatty acid. And then we've also got this little variation, 18:3. So both alpha linolenic and gamma linolenic are both fatty acids that have 18 carbons and 3 double bonds. But what differs about them is the placement of those double bonds. Alpha linolenic has those 3 double bonds. It's an omega-3 fatty acid, whereas gamma linolenic is a omega-6 fatty acid. The placement of those double bonds influences, well, the names, the common names that are used. Um, but that's just kind of one of the things that we talked about. Our general structure for a triacylglycerol looks a little bit like this. Now, where do we find triacylglycerols quite often? Well, they're found in particularly wonderful and delightful foods like peanut butter, as well as chocolate. Now, a fair question out of that is what's one of the, let's take glucose, and I'm going to draw just the basic ring structure for glucose. Yeah, that's it right there. Then we got OH up here, and we got a bunch of OHs. What do all these OHs on glucose and any sugar, what do those typically do? Oh man, that is my worst glucose maybe that I've ever drawn. I have some undergrad teachers who might disagree with that, but what do we, what do all those hydroxide groups make glucose? How do we classify glucose? And I'll lead a little bit more. Polar or non-polar? Absolutely polar. Now, by contrast, what do we know about fatty acids? And we can talk about a triacylglycerol or an individual fatty acid. How would we classify those? Non-polar. Absolutely. When you get those 18 carbons that make up a long hydrocarbon chain, you got something that's really non-polar. So whenever we talk about polarity, is that going to go into solution very well? No, it's not. And then if you think about like, okay, so I pick up this piece of chocolate, I chew it up, and sure, that's got sugars, but it's got fats in there. And as I'm chewing, the pH of my mouth, I can't remember what, I don't know what that is. I don't remember. The pH of my mouth, let's say that it's, 6.5. Then it goes in my esophagus, it's a little bit more acidic, and it goes into my gut, and oh, well, my stomach acid is, or the concentration of acid in my stomach's fairly high. So the pH of the aqueous environment of my stomach is definitely acidic. But does does a non-polar molecule like a hydrocarbon, does that care? Oh, Megan, 6.2 to 7.6. That's a crazy broad range. That's that's a huge range. I feel like, I don't know. Huh, that's interesting. That definitely has to do with what you eat, I would imagine. Lots of other things. That definitely probably impacts dental, oral health, all oral hygiene. Man. Okay, sorry. But now we're talking about non-polar compounds. Does a non-polar compound care that much about the pH of the environment that it's in? This is, thank you, Mackenzie. I'm not sure if you were responding to the look on my face, but this right here, that's my no, probably not face. So when we have this non-polar compounding goes into your stomach, sure, it's acidic, but that non-polar compound, those fatty acids, they kind of don't care about the pH. They don't really care. So then a question is, if you got this fat, or if you have these fatty acids, those fatty acids are going to aggregate together. Those fatty acids are going to arguably kind of form droplets. Now, this right here is a broad overview of what we're going to talk about, kind of the story. Lots of details regarding this story will be addressed in your metabolism class. I'm going to catch up. We're going to talk about the first few parts and talk about the major players, and that will give you a functional knowledge to get us into a discussion of beta oxidation, which is the way in which a fatty acid is broken down and the energy that can be extracted from it. Okay, so this right here is a big picture. Now, this big picture is important overall, but let's get down to the details. What I was kind of alluding to and what I was trying to describe with, oh yeah, you ate that chocolate, that fat, that dietary fat comes in as this nice kind of insoluble glob. Whoa, Joel. That insoluble glob. And it's going to migrate through your gut, and then it's going to get broken down. How does it get broken down? We're going to get into that. So, with that said, fat that enters the stomach is going to trigger the production of bile acids in the liver. Okay. Bile acids. Okay, bile acids are produced in the liver and they are stored in the gallbladder. Okay, so they're produced so that whenever this this dietary fat enters your stomach, this rascal right here, the gallbladder, has those bile acids that can then add them to the stomach to help that dietary fat break down a little bit. Okay, so bile acids first, they're produced in the liver and transported to the gallbladder where they'll stay and they'll wait. They'll keep an ever watchful eye on the contents of your stomach. And whenever they see a dietary fats, they say, go, 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 go. Now, fatty acids. Okay, these saturated and unsaturated fatty acids, we already talked about how those pack together. The unsaturated fatty acids, whether they're mono or polyunsaturated fatty acids, are not going to pack quite as well. What I'm revisiting this for, the purpose that I'm revisiting is we've got this glob, this dietary fat globule. It's almost like a droplet. And that droplet in an aqueous environment is going to stay intact as a droplet. Well, I mentioned bile acids, and a fair question is what the heck is a bile acid? I'm not sure if anyone's watching this and thinking, like, man, the way that he said, what the heck, I thought he was going to drop the F bomb or something like that. I'm going to do my best not to do that. But what on earth is a bile acid? Well, I'll tell you. But in order to give you that story, we need to go back to our discussion of lipids and the different types of lipids. We had our classifications of lipids, the different classes of lipids, fatty acids, triacylglycerols, glycerophospholipids, sphingolipids, steroids. What was our big steroid that we talked about, or what was kind of the important steroid that was a couple of rings? Cholesterol. Cholesterol has a general structure where we've got three six-membered rings and one five-membered ring. Cholesterol is the most common steroid in animals and a precursor to all other steroids. Okay, that's an important point right there because this structure right here, these four rings, well, they are used to produce bile acids. Sometimes you'll hear the term either bile salt or you'll hear bile. And bile is going to act, or bile acids are going to act as detergents. And if you think about detergents, if you did anyone learn add a Y or an N for this? Did anyone learn the term detergent when you took organic? Wonderful. I think that whenever I heard the a detergent for the first time, I remember hearing it and thinking, "Oh, okay, it breaks up like junk that I get on my hand. It kind of inserts itself to disrupt things. It disrupts, or bile acids can disrupt my cells. Sorry about that. These bile acids and bile salts, they're stored in the gallbladder, produced in the liver, stored in the gallbladder, and these are places where they have some sort of modification. Now, I don't need you to know these groups, but our major bile acids are, okay, there we go. Cholic acid, glycolic acid, and taurocholic acid. Chenodeoxycholic acid, glycochenodeoxy acid, and taurochenodeoxy acid. What I want to stress is we got the same general structure, but we've got a modification here and here. I don't need you to know these structures or these names. What I want you to know is that bile acids and bile salts are, well, these are terms used for a kind of a broad range of different compounds. And these R's, so this R2, for example, if at R2 we had OH, and then at R1 we had, again, let me erase that. If we had OH, that molecule that I've just kind of drawn with those OHs, that would be cholic acid. If by comparison we had at R1 we had simply a hydrogen, that would be chenodeoxycholic acid. So the significance of these names, it's not super important, but these are different these are different compounds that are used as detergents to help break up things like micelles of your dietary fatty acids. They'll cluster together, but then these bile acids kind of insert themselves to help break up the whole system. They help solubilize those individual components. Okay, so what we've got is our dietary fat that has made its way into the stomach. And then these little black droplets right here, here, what they're going to do is they're going to help that dietary fat break into smaller pieces. So these bile acids and these bile salts are going to help that take place. And whenever they're helping that take place, notice these large lipid droplets, when they're in closer proximity to these bile salts, what they're going to do is they're going to get to even smaller pieces. And these smaller pieces will form smaller and smaller, progressively smaller and smaller micelles. Okay. Now, those smaller micelles will ultimately get to a point where, thankfully, we can use micelles to break them up. Now, all the while, this dietary fat, and just in case I said something that kind of confused or distracted you, think about this as mostly this is triacylglycerols. So we haven't done anything to really break down these triacylglycerols. Most of your dietary fat is a triacyl or is dietary. Most of your dietary fat is in the form of triacylglycerols. Will you consume or ingest some fatty acids? Yes. But these droplets right here and right here, those are micelles made up of triacylglycerols. Okay. Now, these progressively smaller and smaller micelles, largely made up of triacylglycerols, will ultimately get to a point where in an intestinal epithelial cell, it'll be broken down into individual triacylglycerols. And that's when we have a process known as enzymatic hydrolysis. Now, if you remember this slide, the last thing that we talked about on the other side of it, could anyone add to the chat what was where my X? What did I write there? Or what did we describe in that X position? Either the process or yeah, the process. What was that process called? Where I have my X written. What was that called? Saponification. Perfect. That saponification is the industrial process by breaking down a triacylglycerol. Okay, just before I proceed, can I get a on a scale of 1 to 3, 1 being I'm totally lost, 3 being I'm feeling all right, let's proceed. Can I get a response from everyone? Okay. I just got a question. 2 point. I was leaning towards whole numbers, but I respect that. What do the biles do? The bile salts, the bile acids. I'm going to jump back. Essentially, what these things are going to do, what I've just put a big circle around, is they are going to kind of insert themselves into these micelles. And that's going to cause them to grow a little bit, but help them um, either grow to the point where they break into smaller micelles, or at very least give a little bit more space for an intestinal lipase, an enzyme to come in to extract those individual triacylglycerols. I hope that answers the question. If not, let me know. Okay, I'm getting okay, 2s and 3s. Okay, good, 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 good. Now, 14, 15. Okay, there we go. Saponification, that's the industrial complement. But I gotta be honest, I'm a human. I'm an animal. I'm more interested in this enzymatic hydrolysis. Okay, so with that in mind, though, we've got these, let's say that we've got a micelle. It's a spherical molecule, lots of triacylglycerols. We've got some bile acids in there. But how do I go from that? So here's my triacylglycerols. And then in an intestinal epithelial cell, I'm going to break that down into individual fatty acids. That seems like quite a bit of a jump. How am I going to go from that triacylglycerol in an aqueous environment where it doesn't like to be to an individual fatty acid, where again, that individual fatty acid isn't going to enjoy being there? The question is, or let me rephrase all of that. The question is, how do we get something that is an insoluble nonpolar compound in a polar environment to be broken up? Well, we know with an intestinal lipase, a lipase is going to do that. But kind of how? Because if you've got a super hydrophobic molecule, is that going to want to work with an enzyme that is probably going to be fairly hydrophilic? Not really. A hydrophobic compound is not going to want to work with a hydrophilic enzyme. So, how do enzymes deal with these big chunks of lipids? Lipids are insoluble in water. Enzymes are generally soluble proteins. So, if you think back to, I think, maybe you first learn about this in like Chem 1, like dissolves like, and then you definitely will learn about it in organic, like dissolves like. These two things are kind of from opposite worlds. A soluble protein and an insoluble lipid. It's cliche, but it's oil and water. They're not going to want to mix with one another. So how do they mix? Well, what it boils down to is this model right here. And this is definitely a complex idea. What I want you to take away from this is I want you to know the players, and I want you to know the specific region where this activation takes place. So at the top where I have my star, this is an enzyme. This is a lipase. What this lipase is going to do is it's going to take a triacylglycerol and break it down into glycerol and three fatty acids. Can I get a Y in the chat or an N? A Y if you're good, and N if no, I don't follow that. Okay. Lots of Y's. So we've got our protein there. And all that that thing does is it takes on the circled thing is the lipase. Yes, absolutely. And what it does is this reaction tag equals 3FA plus glycerol. So that's what it's going to do. It's going to jump on a TAG and take three fatty acids and one glycerol and release it. That's what it's going to do. But this tag is a part of a micelle. Okay, so now what I'd like to do is bring you down here to where I'm going to draw another star. I'm going to erase the first star and I'm going to erase my big circle. Now this green, where you see all these head groups, where you see all these, those are our triacylglycerols. TAG. I'll say S, tags. What that protein, and then here is, I'm going to circle my lipase. The tags of the micelle, what's going to happen is our protein, our lipase, is going to undergo a shape change. It has a lid. It has a part of its amino acid chain that is referred to as its lid. It's this yellow region. I'm going to put the letter Y by it. That yellow region, that lid, is going to open up to expose an internal cavity of that protein or an internal region of that protein that is, lo and behold, hydrophobic. That is the active site of our protein. So it's almost like, let's imagine that my hands right here are the lipase. Let's say that my arms are the lipase. What's going to happen is my hands are going to open up and the palms of my hands are extremely hydrophobic. If we've got a triacylglycerol, I'm going to jump back. This right here, well, that's going to be pretty darn nonpolar. Another way of describing that as nonpolar is to say that it's H-phobic, hydrophobic. So this lipase kind of is like, hey, what's going on, my cell? Oh, you're a collection of triacylglycerols? That's fantastic. No, I'm not going to take individuals of you and break you into glycerol and three fatty acids. I am. That glycerol, those glycerol head groups are none the wiser. So this portion of our protein opens up and exposes a hydrophobic active site. Now, to follow that up, and I'm going to revisit this in just a second, we have something known as the interfacial action. This is the lipid water interface. And this to me is pretty cool because essentially what it is our lipase has a sensitivity to it. It's able to detect, okay, it's almost like it's able to detect, okay, here's a water molecule. On the other side of that water molecule, well, that's a glycerol molecule, a glycerol head group. So I've got like a friendly group, my water molecule, but then just on the other side of that is glycerol. I've got this wall of waters, but then I've got glycerol. Okay, so lipases exhibit interfacial activation, meaning their enzymatic activity increases when they come into contact with that lipid water interface. Water interface. This is particularly important in the context of fat digestion, where lipases act at the surface of lipid droplets. Okay, can I get a Y or an N if you follow that? I'm going to jump back. A Y for got it, and an N for wait. What were the players? Okay. Okay, great. So I want you to know that term, interfacial activation. That is essentially this enzyme detects this boundary, this barrier, this separation. So that brings us down here in this region that I've highlighted in red, where basically lipases are going to take those triacylglycerols and blow them up. They're going to take those micelle, or they're going to, yeah, take those small micelle lipid droplets, blow those triacylglycerols that make them up into individuals, and then in something like an intestinal epithelial cell, what I've circled in red right now, okay, so what I've circled in red right here, this is individual fatty acids. Okay, those individual fatty acids can be transported into an epithelial cell. Those individual fatty acids can then be, this is going to sound strange, but it's important and it does take place. Those individual fatty acids get reassembled into triacylglycerols. So they get repackaged into triacylglycerols. That seems a little bit like, well, why did we break up triacylglycerols only to remake those triacylglycerols? Well, one thing is that this is dietary fat right here. It's a, it's not simply being blown straight through into the circulatory system. Instead, what is happening is this intestinal epithelial cell right here. I'm going to erase that circle and that circle. When those micelles are broken up into individual fatty acids, those intestinal epithelial cells receive those individual fatty acids. And then they say, okay, cool, I've got the parts so that I can make a triacylglycerol. And whenever I do that, I'm going to package them together and I'm going to send them out. That's a way that the body is going to regulate the amount of triacylglycerols, the amount of fatty acids that are in the bloodstream, and process them accordingly. Now, the fate of these. Okay, actually, before I proceed, does everyone follow that we have this process? Tags to FA, fatty acids, to fatty acids, but now I'm going to say in the intestinal IEC, the intestinal epithelial cell, and those triacylglycerols get reassembled, or sorry, those fatty acids get reassembled into triacylglycerols. The tags get turned into, this would be in the, I believe it's called the intestinal lumen. So that's just kind of like still within the like aqueous cavity of the small intestine. So in the interior, and then not within the cells of the small intestine. Does that answer your question? Absolutely. Okay. Is everyone good with this? Give me a Y or an N. Okay. 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 Great. So when the intestinal epithelial cells have repackaged and they've kind of said, okay, well, you've given me the resources. Now I'm going to make these triacylglycerols and then I can distribute them. That's when they go to tons of different places. Now, with that in mind, what are the fates of these? Well, some of them are going to go to muscle cells. Some will go to adipose tissue. Some will go to the liver. And they'll make their way into a couple of different compounds: VLDLs, IDL, HDL, very low density lipoproteins, high density lipoproteins, intermediate density lipoproteins. These are things that, again, you're going to get more of whenever you take metabolism. VLDL, HDL, LDL, IDL. These are things that you've maybe got a little bit of exposure to from either yourself or a family member getting an annual physical, or maybe they say, "Oh, my LDLs are high, so I need to do this," or "My VLDLs are low, this is what I need to do." Um, where we're going to go from this is, what about when we actually take those kind of home brewed triacylglycerols? So the ones that our intestinal epithelial cells have reassembled. Um, how do we deal with those? What do we do with them? Well, we've got a way in which this is going to take place, and where we're going to see some of these fatty acids that are distributed to the bloodstream. So on the left hand side, we've got an adipocyte, and on the right hand side, we have a myocyte. Okay, so these triacylglycerols can reassemble into a lipid droplet within a fat cell, like an adipocyte. Now, this is reflecting what is known as a hormone sensitive lipase. That's player number 3 right here. Okay, now there's a lot going on here, but we're going to work through it pretty deliberately. So, our hormone that we're referencing is either going to be epinephrine or glucagon. Those are two hormones that will essentially lead to or they will inspire burning fat. So, in an adipocyte, which here's our adipose tissue. So, we're essentially right here. That's where we're catching this story back up again. We've got a lipid droplet that's in an adipocyte, and lo and behold, let's say glucagon shows up. Glucagon is the hormone that is perceived by a receptor protein. This is a membrane protein that will basically bind something exterior, and it will signal a response. What this receptor protein will do is it's going to activate an enzyme known as adenylyl cyclase. Adenylyl cyclase will take ATP and make cyclic AMP. Cyclic AMP is a secondary messenger, and what it's going to do is activate an enzyme known as PKA, or protein kinase A. Okay, so what has happened in this adipocyte? This adipocyte has fat or lipid droplets in it, and what's going to happen is glucagon is going to be perceived by this receptor protein that activates another enzyme known as adenylyl cyclase. Adenylyl cyclase will take ATP and convert it to cyclic AMP. Cyclic AMP is then going to activate protein kinase A, which is going to do two things. One thing that it's going to do is it's going to transfer a phosphate group onto our hormone sensitive lipase. And I'm going to label this as HSL active. it's going to cause it to relocalize to this lipid droplet. So hormone sensitive lipase gets phosphorylated and moves to the lipid droplet. Phosphorylated hormone sensitive lipase will then find that protein kinase A has done something else. Protein kinase A has phosphorylated a number of other proteins to basically help out with taking triacylglycerol, these perilipins. These are proteins that will aid in aid the hormone sensitive lipase in its main objective of taking triacylglycerol, those in-house triacylglycerols that have been synthesized, and break them down into individual fatty acids. So free fatty acids in an adipocyte will then be trafficked to the bloodstream where they can then jump into the bloodstream and go to another cell like a myocyte. A fatty acid transporter on a myocyte will then see a free fatty acid and say, well, come on in here. You're welcome here. And that free fatty acid within that myocyte will undergo the process known as beta oxidation. And that beta oxidation is where we're going to break that fatty acid down into, well, CO2, but more importantly, we're going to get a bunch of ATP out of it. Now, right here, you might be thinking, oh, this is a lot of information. It's pretty darn interesting, but it's a lot of information. What do I need to know right now? And what do I need to know for my exam? What I need you to know and what I want you to know is that this is what's known as a signaling cascade. The receptor does not bring glucagon into the cell. So hormone stays out. That's one thing that I need you to know. How? Well, the R protein perceives it. Perceives. Perceives it. The it here being the glucagon. Then the R protein activates adenylyl. Let me move this up a little bit. Adenylyl cyclase. That adenylyl cyclase will make our secondary messenger. That secondary messenger activates pKa, and pKa essentially enables HSL, or hormone sensitive lipase, to get, just a second, to get FA into bloodstream. So the big players are glucagon, the receptor protein, adenylyl cyclase, cyclic AMP, our secondary messenger, and pKa and HSL. So that's a lot of information, but those are the important parties that I want you to know for this. Now, the second part of this, those free fatty acids, when they're in the bloodstream, well, they have a fatty acid transporter. These fatty acid transporters enable those free fatty acids to undergo beta oxidation. So, does anyone have any questions about this right here? If you're good with this and good with the details that you need to know, please add a Y to the chat. Okay, great. So the reason that I left that fatty acid transporter and lots of stuff over to to be dealt with, and I didn't include that in the details that I kind of went. What were the two things that PKA did? Great question. I got that as a private message. PKA is doing two things. One of them is it's helping hormone sensitive lipase, it's activating hormone sensitive lipase. It phosphorylates hormone sensitive lipase, and it's almost like hormone sensitive lipase is like this. It's in the cytosol, and it's like, okay, well, time's gonna come. Oh, then it gets phosphorylated and says, oh, I've been phosphorylated. I shouldn't be right here. I need to be over here, where there is a lipid droplet. That's one thing that PKA does. The other thing that PKA does is it's going to be phosphorylating this perilipin. Perilipin is a protein that aids in the recruitment of hormone sensitive lipase and the subsequent transport of those triacylglycerols as individual fatty acids into the cytosol and then into the bloodstream. I hope that answered your question. If not, follow up. Okay, so now what I'm going to do, we've got all that, is we're going to get into this fatty acid transporter stuff. What's going on there? Now, the glycerol portion of that fatty acid, we'll get to that in a second. What that's going to do is that's going to go to the liver. And whenever it goes to the liver, well, we can use that to make, through gluconeogenesis, that glycerol is going to find its way to make dihydroxyacetone phosphate, to make glucose. The point here is glycerol is going to go to the liver so that it can be used for gluconeogenesis. Glycerol produced in that adipocyte doesn't do too much, so we need to get that to the liver. Yeah, and if not, it can either go to the brain or it can be recycled as lactate for the muscle. Okay, now here we've got our free fatty acids. In order for a fatty acid to be metabolized, what we need to do is we need to activate a free fatty acid, a free FA. We need to use a coenzyme A molecule, or CoA. We need to use ATP. And from that, we're going to get this right here, FA CoA. Okay, now this is irreversible in vivo, because what we're going to do is we're going to make in the process here. Look at this. ATP, what is the fate of that ATP? Well, it's going to end up as AMP and PPI. Now, you might be thinking, okay, well, I follow you. AMP is adenosine monophosphate. PPI, well, is that two individual phosphate? No, but PPI looks like this. I haven't drawn, I'm going to draw all my negative signs, but that's what inorganic pyrophosphate is. And that has a high energy bond. And when that breaks, it breaks down into two individual phosphate molecules. So that will break, that will be hydrolyzed, and it will give us two PI molecules. Now, a fair question is, well, what does FA CoA look like? This whole thing right here. So what I've got kind of as a box right here, or within this box, this is your fatty acid. That fatty acid or that free fatty acid has been added to basically this whole thing right here. What I've got a big circle around right there is our CoA. So FA plus CoA is that whole thing. So we need to activate free fatty acids so that they can be burned. Now, an important thing to know, they are holding hands. I like that. Lipid oxidation. Oxidation is our breakdown. That's going to occur in the mitochondria. So we put this in the, what was it? It wasn't an adipocyte, it was a myocyte. But we got to get it in the mitochondria because that's where our breakdown is going to take place. Synthesis is going to take place in the cytosol or in the cytoplasm. I use those two terms interchangeably. Now, if anyone is drinking a Monster Energy drink, or maybe they take a dietary supplement, or like a hydroxy cut was one a long time ago. Carnitine. Carnitine is a non-essential amino acid. And what carnitine does is it helps take an FA CoA. That's what this is. This is an activated fatty acid. It takes an activated fatty acid that is found within the cytosol of a myocyte. It takes this FA. That's what we need to do. We need to move this long hydrocarbon chain from the cytosol into the mitochondria. Because if you remember, the mitochondria has two membranes, and the inner one is super, it's almost like a, well, it's basically very, very selective. Now, we use this enzyme, carnitine, or sorry, we use this amino acid, carnitine, and this enzyme, carnitine palmitoyl transferase 1, to move this FA from an FA CoA, and we transfer that FA onto carnitine to make FA carnitine. So our activated fatty acid, FA CoA, we take the FA, add it to carnitine, and that's kind of the, well, it serves as a substrate for this transport protein known as the carnitine carrier protein. That protein is going to say, "Oh, carnitine and anything that's bound to it, I'm going to move you into the mitochondria." And that's where we get this FA carnitine. Now, in order for this fatty acid, that FA, to be broken down, well, is it ready to go? Not quite. We instead need to take this FA and remake FA CoA. That FA CoA can then go on to be metabolized. Now, with that in mind, is there any part of this that sounds kind of familiar? And not necessarily, uh, whenever I say familiar, I mean this sort of modeling of, hey, we need to move this molecule from one side of the membrane to another side of the membrane. It's not changing. We just have to, or the molecule isn't being broken down or anything. Psh, psh. Absolutely, RP. That's what I was talking about. That's what I was thinking about. Going from pyruvate, our last step, back to phosphoenol pyruvate through gluconeogenesis. We package it up, we send it into the mitochondria so we can make oxaloacetate to make malate, malate to then go out, remake oxaloacetate, then go on to make phosphoenol pyruvate. So we have the same sort of thing. Like this molecule, we just need to get these carbons from this side of the membrane to this side of the membrane. How do we do that? Well, we use this carnitine transfer system. And sometimes you'll hear of this referred to as the carnitine transfer system. Sorry, for just a moment, I had a scare that I wasn't recording any of this, but here we're good. Okay, so carnitine palmitoyl transferase, or carnitine, is a non-essential amino, not non-essential. It is a non-proteinogenic amino acid that's involved in fatty acid metabolism. Because the idea is carnitine, if you've got that, well, then you're going to be able to move fatty acids into the mitochondria. That's one of the reasons that if you look at the ingredients for a Monster Energy drink or a Red Bull, I think that it's in both of those, or Rain, or any of those other energy drinks. One of the things that you'll probably see is carnitine on there. A great question from that is, well, is that carnitine actually going to assist in any of this? I mean, when you ingest it and it goes to your stomach, is that gonna materialize in anything? And I don't know the answer to that, but that's a great question. Okay, can I get a Y or an N? A Y if you're good, an N if I'm a little bit flustered or flummoxed by the carnitine transfer system. Okay, okay, great. Now, one little detail is that carnitine acyl transferase, or this acyl transferase is also known as um, acyl, is kind of a filler for a long hydrocarbon chain. So carnitine acyl transferase 1, that is a name for, just think about that as carnitine transferase 1. Acyl and palmitoyl, palmitoyl is in reference to the length of the fatty acid chain. So carnitine transferase 1 is inhibited by this molecule malonyl CoA. Malonyl CoA is used for fatty acid synthesis. I just bring this up and I just highlight this because of the fact that, well, if you're breaking down fats, do you simultaneously want to be making fats? No, you don't. Why would you do that? If you've got fatty acids available, well, then you don't need to make any more. Likewise, if you're trying to make fatty acids, then you want to stop the breakdown of them. Now, that's not a detail that I want you to know. What I want you to know from this is I want you to know that the activated FA-CoA is what gets linked up to carnitine to get it transported into the mitochondria. And then carnitine is released, free carnitine goes back. Okay, here's where we are. This is where we need to be. This is in the mitochondria. What we needed to do was we needed to get fatty acyl CoA, that one at the top, into the mitochondria. Good news, everyone, we're in the mitochondria. Now, when it comes to everything that stems from this, oh, not what I wanted to do. Boop, 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 boop. There we go. This is an activated FA in the mitochondria. Now, for the time being, what I'm going to do is I'm going to scribble out all of this. Because what I want you guys to focus on is the kind of vertical portion of this slide. Fatty acyl CoA. Acyl. That's just saying that we've got some fatty acid that's activated with how many carbons? How long is this carbon chain? N. It could be 13, it could be 35, it could be 9. It's basically anything 5 or more. Now, the 5 isn't so significant, but it's important, or it will be a little bit more apparent why I said 5 in just a moment. Okay. So this is a process where we're going to be breaking down a fatty acyl CoA into a fatty acyl CoA that's 2 carbons shorter and an acetyl CoA molecule. Okay? Acetyl CoA. This is a molecule that I want you guys to be able to understand what it is and what it looks like. It's effectively 2 carbons. Why do I say that it's 2 carbons? Because the other part of it is this coenzyme A. Have we seen that coenzyme A before? Answer that question. Have we seen coenzyme A perhaps earlier today? You can add a Y or an N for that one. Yeah, we have. Where did we see it? We saw it when we were activating our fatty acids. We had CoA plus ATP plus our fatty acid gave us our activated CoA. So whenever we're down to a FA that's 2 carbons long, those 2 carbons plus coenzyme A make up acetyl CoA. So is everyone good? Give me a Y or an N if you're good with acetyl CoA, what that molecule looks like and effectively where those carbons are. Okay. So we're going to take a fatty acyl CoA and we're going to break it down into acetyl CoA. Now, what I want you guys to do is I'm going to do this on the right-hand side of the screen. And I'm going to start with a fatty acid that looks like this. S-CoA. How long is this fatty acid? It's 5 carbons long. Did we count our carbonyl carbon in that count? We did. Do we always count our carbonyl carbon whenever it comes to counting up the number of carbons in a fatty acid chain? We do. Now, this is my alpha carbon. This is my beta carbon. Our first step in beta oxidation, what it's going to do is it's going to do an oxidation reduction reaction. We're going to take FAD and we're going to make FADH2, and we are going to add a double bond between, well, let's see, our alpha and beta carbons. So here's my carbonyl carbon, my alpha, my beta, my carbonyl carbon, my alpha, my beta. So my product, sorry, I had to itch my leg, looks like this: CH3, CH2, CH, and I'll actually draw that H going downward. Doesn't matter. I could have drawn it downward or upward. I was really just doing it for organization. CH, and then C, carbonyl carbon, and S, CoA. Okay, so that's going to give us a molecule with a double bond in there. At this point in time, we've taken a saturated fatty acid and made a mono unsaturated fatty acid. Whenever we do that, the next step that we're going to follow through on is going to break that double bond with a hydrolysis reaction. We're going to use the enzyme known as enoyl-CoA hydratase. And what we're going to do there is we're going to add a hydroxide group on my beta carbon. We're going to add water across that bond. So we've got CH3, CH2, COH, H. We've got a single bond now, H2, S-CoA. We've made 3L-hydroxyacyl-CoA. Is everyone good with what we've seen so far? Add a Y or an N for that. Okay. So what materials have we used and what have we generated? One thing that we've generated is FADH2. Now that FADH2 is going to be just like, well, what's another electron, or sorry, FADH2 is a nucleotide that is an electron carrier. Whenever we were going through glycolysis, we made a nucleotide that is an electron carrier. Which molecule was that? Spoiler, we made two of them. Spoiler, there we go. We got NAD plus, but I'm actually going to correct that, NADH, because NAD plus is going to be your oxidized form, and NADH is your reduced form. So NADH is what we made in glycolysis. FADH2 we make in beta oxidation. We've made one NADH or FADH2 molecule. We've also used water. We made that 3L-hydroxyacyl-CoA. And now what we're going to do is we're going to take where that double or that hydroxide group is, and we're going to make that a carbonyl oxygen. So CH3, CH2, C, CH2, C, double bond, then S-CoA. And that gives us a molecule known as beta ketoacyl CoA. Looking at that beta ketoacyl CoA, does anyone see where there's kind of a natural place where we can chop off two carbons? Y or N. You don't have to awkwardly describe what that is. Does anyone see a kind of natural like cut? Oh, if I broke this bond, then I'd release two carbons, and then I'd release another part of a molecule. methyl group. Okay. Where I'm looking is, and what I want you guys to recognize, and I'm sorry for my kind of leading question, was here's a carbonyl carbon. Here's another carbonyl carbon. They look kind of similar to one another. This carbonyl carbon right here that I've just put a star underneath, well, if I used coenzyme A, S-CoA, just kind of cram that in there, well, then I break this bond right here. And then I could end up with H3, and that's where I get one acetyl-CoA molecule and then another resulting molecule, or a compound that's basically 2 carbons long, or two shorter, I'm sorry. Does everyone follow what I did there? Add a Y or an N. And if it doesn't make a lot of sense, then that's fine. Just let me know. Yes, we added another coenzyme A. Effectively, you could kind of think about it as we took a molecule where there was coenzyme A bound, and we just activated another part of the same chain. So we in OChem 2, we learned about oxidation of beta keto acid. Is this similar? I believe that it is. Yes, yes, yes. Now, what else is taking place? And just to kind of rewind for a second, we talked about we made FADH2. We used water for this process. What else did we make? Well, we made NADH. And I kind of, where my drawing that I just did a moment ago, where I put that other coenzyme A molecule, I kind of skipped, not really skipped, but I drew but didn't explicitly state what was taking place here. This is our beta keto acyl CoA thiolase. We're using a sulfur, a thiol group to break a bond. So we're going to generate an acetyl CoA. Now, we started with a 5 carbon molecule. We now have a 3 carbon CoA. Let me ask you this question. If instead of starting with I'm going to, up at the top here, where I got my 5 carbon molecule, I'm going to erase this. And I'm going to say, what if instead of starting with a 5 carbon molecule, oh, dang it. I started instead with a 4 carbon molecule. Tell me how my products would be different. Perhaps a good lead for that what would my products be? Think about, where did I add my double bonded oxygen? Or where did I make my second carbonyl carbon? I'm going to let you guys simmer on that for a second. Okay, now I'm going to add a little bit more of an idea. 2 carbons each instead. Would they not be the same, but one less carbon? Yes, they would. And what do we call that molecule that's 2 carbons plus a CoA? Acetyl cow? Close, I like it. Acetyl CoA. Absolutely right. And if you're thinking, yes, that was a very impressive cow sound that I made. I like it. I feel like that is going to go worldwide now. So, my point is, If you take a even carbon numbered fatty acid, you're going to pluck off acetyl CoA. Once you get down to a molecule that's 4 carbons long, you're going to go through that and release two acetyl CoA molecules. So my products would effectively look like that and that. Now, the significance of this is those two acetyl CoA molecules, those can get plugged into, because it's taking place in the mitochondria, they can get plugged into the electron transport chain and the citric acid cycle and the electron transport chain. And from that, we're going to generate tons of NADH. Now, over the next few slides, this is effectively the same thing, but with a little bit more detail. There are, this is, yeah, this slide right here is effectively the same thing, showing each one of the components breaking off. The same enzymes, the same players involved. Where I scribbled everything out at the top, I intentionally did that because it's a little bit of it's not necessarily a mess, but it's a lot of information. What I want you guys to take away from this is that we've got FADH2, NADH, and acetyl CoA. Those are the products from one round of beta oxidation. One FADH2, one NADH, and one acetyl CoA. Those are our 3 products. Which you might think, oh, well, that's swell. That's neat. We get 2 different electron carriers and an acetyl CoA molecule that we can plug into the citric acid cycle. Swell. Now, this is another little bit of detail. Mitochondria have 4 different acyl CoA dehydrogenases used for different lengths of fatty acids. A deficiency of medium chain acyl CoA dehydrogenase is associated with SIDS, approximately 10% of the cases. Now, this beta oxidation is taking place in the mitochondria. If we take a 4-carbon long Fa CoA, what are we going to get? We're going to get 2 acetyl CoAs. What else are we going to get? We're going to get 2 NADH. What else are we going to get? 2 FADH2. Is everyone good with those numbers? Add a Y or an N to the chat. Okay. Now, if you have a fatty acid that's 16 carbons long, and actually, before I do that, how many rounds of beta oxidation will a 4-carbon long fatty acid take? Add to the chat your answer. 1. Spot on. It will take 1 round. Now, before you answer this question, think about what are the products. Let's say we have a 6-carbon long fatty acid, Fa CoA. From our first round of beta oxidation of a 6-carbon long fatty acid, or Fa CoA, we're going to get a 4-carbon long fatty acid, Fa CoA, and acetyl CoA, NADH, FADH2. How many rounds of beta oxidation are required to break down into just acetyl CoA a 6-carbon long Fa CoA? This seems like, oh, well, it's got to be 3. Spoiler, it's not. 2. You're absolutely right. Because your first round will get it down to 4 carbons. And then that 4-carbon long fatty acid CoA will be broken down into your 2 acetyl CoAs. So there are only 2 rounds. So then let's jump this up to 18-carbon long Fa CoA. How many rounds of beta oxidation are required for an 18 carbon long Fa-CoA? To break that down completely. 7. Because you're getting 2 carbons. Wait, 7. No, it's going to be 8. 8 is the correct answer. Because round 1, or your last round, will get you your 4 carbon down into 2 A-CoAs. So the players that are involved in breaking these things down, acetyl-CoA, NADH, FADH2. Okay, cool. But where is this talk of a fatty acid gives you a lot of energy? 16 carbon long fatty acid. From a 16 carbon long fatty acid, you will do 7 rounds of beta oxidation. How many ATP will you get from it? Well, those FADH2s that you generate from each round, there are 7 rounds, so you'll get 7 FADH2s. You'll make 14 ATP. Ooh, that's pretty good. Is that better than one 6-carbon glucose molecule? Yeah, it is. Because one 6-carbon glucose molecule that you're gonna from glycolysis alone, you're only gonna get your net 2 ATP. And of course, that's not the end of the story, but that's part of the story. You're gonna get 7 NADH. From that, you'll generate 21 ATP. So we're at a total of 35 ATP generated. From your 7 rounds of beta oxidation, you are ending up with 8 acetyl-CoA molecules. Because remember, when you get down to that 4-carbon long molecule, acetyl-CoA, acetyl-CoA. Those 8 acetyl-CoA will be used in the citric acid cycle to make 8 GTP, which is effectively the same as ATP. You will also make NADH, 24 of them. Those 24 NADH will be used to make 72 ATP. You'll make 8 FADH2, and from those 8 FADH2, you'll make 16 ATP. All told, from the complete beta oxidation of a palmitic acid, which is a saturated fatty acid, 16 carbons, 0 double bonds, you will generate 131 ATP. But then you got to remember what was involved in the activation of that to take that Fa to make Fa-CoA, because you did invest. Well, subtract 2 ATP, you'll make 129 ATP from a 16 carbon long fatty acid. So when you look at this and you think about it as, maybe you're thinking about sugar, like glucose, like drinking eating a Starburst or something. Yeah, that has calories in it. Sure does. Fats. Yeah, there's a caloric measurement of those. This is energy that you're generating from those different molecules. 16 carbons in a fatty acid is going to yield more ATP than 16, the same number of carbons found in a sugar. So from all of these 16 carbons, you're getting a total of 129 ATP. What I want you to know, and what I want you to be able to answer, is I want you to know, depending on the number of carbons in that molecule, how many rounds of beta oxidation will you do? Then what I want you to know is how many acetyl-CoA are going to be generated. I want you to know basically these numbers and how they translate. So if I gave you a question on an exam that was something like, 12, 0, how much ATP is going to be generated from that? Well, whatever your number is, you're going to subtract 2. But you would also look at this and say, okay, let's see. So a 12 carbon long fatty acid, 12 divided by 2 would be 6. That means I'm doing 5 rounds. That means that I'm going to get, 5. I changed my numbers here. erase that. I'm going to get 5, 5, 6, 6, 18, 6, which is going to lead to me saying, well, I double this number. 1 FADH2 yields 2 ATP, so I'm looking at 10. 1 NADH yields 3 ATP, so I'm looking at 15. 6 acetyl-CoA, that's going to give me 6 GTP, which is the same as 6 ATP. 18, well, I multiply that by 3 NADH because 1 NADH is 3. So I'm looking at 54. 6, and that would be multiplied by 2, so I'm talking about 12. So a 12 carbon long fatty acid, completely saturated, that's 25, 31, 85, 97 minus 2. If anyone, I feel confident about my math, 95 ATP are going to be generated from that. Can anyone check to see if I'm incorrect there? Great. Thanks for the backup, Mackenzie. Does that number change if you're talking about an unsaturated fatty acid? 100%. And to illustrate that point, let me ask you this. Is this fatty acid saturated or unsaturated? Add an S for a saturated, a U for an unsaturated. Totally saturated. Okay. So we got an S there. And what do we do very first? We add a double bond. Well, if it's a monounsaturated fatty acid, you're down. You don't need to make that an FADH2. So an unsaturated fatty acid is going to get you less energy. Okay, that's what I got. I'm sorry I stole at least 2 of your minutes. I'm going to end. I'm going to stop my share right there. I'm going to stop my recording right here.